Professor can record the class? Oh.
So we looked at big T last time, the unit tangent vector, and then we looked at an orthogonal vector to big T, big N, and big N can be found also, but you have to find big T first, because big N is the unitized derivative of big T. So I want to say something about big N. We know that big T is the unitized velocity vector. A lot of students who are new to this go, oh, I know, big N is simply going to be the acceleration vector unitized. Oh, no, it isn't. No, 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 no. Not even close. Like, oh, it'll be good enough for government work and I'll get it sort of right. No, you won't, because it ain't the acceleration vector unitized. Well, it's based on the derivative of big T. Yes, that's true. But you'll notice if you do both, like you can go ahead and try and get the unitized acceleration vector and compare it with big N. And you're going to see they're not the same. So please do not go down that tunnel, because there's no cheese at the end of that tube, okay? No cheese at the end of that tunnel. So please don't. So big N is you first have to find big T, and then once you do find big T, which is unitized velocity, then you go get big T's prime and unitize that. And it's not the acceleration vector unitized. Good luck if you think it is.
Oh, Professor?
Yeah.
So in my math lab, they give different formulas to find T and N.
Mm-hmm. And you're not going to use them.
All right.
You're going to use mine because they're easier. Okay? So please do it my way, and you'll thank me later. Okay, so what we found last time is one of the uses of acceleration and velocity and speed and all that stuff is, well, speed anyway, is arc length. So arc length, which is denoted little s in mathematics, can be found by taking the integral going from A to B.
My car is dead. Can I use your car?
Oh my God, are you serious?
No, but can I use your
Excuse
car?
me. Yes, you can.
I don't know what keys are in it.
Okay. So arc length was the integral of speed, and then there was something called an arc length function, which can be used to parameterize a curve. So usually this lower limit is 0, but it doesn't have to be. And then you integrate your speed again, and you can use that to reparameterize your vector valued function. So that's kind of nice. So we looked at some examples of that, and this is going to come into play in a moment. So now let's talk about a new topic. So let's talk about curvature. So one of the things they use for arc length parameter, it's an application, is to find curvature. It's how sharply a curve bends, how curly it is or curvy it is. So take a look at this curve. I hope you would agree that here at point P, it's got more curve to it than over here at point Q. At point Q, it almost looks like it's straight, like there's no curve to it. Yeah. So how do you come up with this idea of measuring curvature? Like, how did the mathematicians do it? Well, if you look at big T, now you know what big T is, it's the unitized velocity vector. At various points that are near P, you'll notice that you know, it's always tangent. So you'll notice it's like pointing this way at first, then it looks like it's pointing up, and now it looks like it's sort of pointing over to the right. So it's changing pretty rapidly as it moves around the curve that's close to the point P. On the other hand, if you were to look at the tangent vectors over here near Q, they're not changing direction very much. They're mostly pointing in the same direction, like to the right horizontally. So those unit tangent vectors aren't changing direction much. So what they decided is they're going to calculate curvature by calculating the rate of change of the unit tangent vector and then taking the magnitude of that and the rate of change of the unit tangent vector with respect to the arc length. So here is one formula that you can use for curvature. And so Dominic, for curvature, I'm going to give you more than one formula, and you can use any of those formulas, whichever one you think is easiest.
Sounds good.
So this one, This one is limited though, the one I just put here on the screen, because, and here's some other notation for it. It's limited because you can only use it if your vector valued function is even parameterized using that arc length parameter. So if it isn't, you can't use this formula I just put on the board. So it has to be parameterized using the arc length parameter, where your big T of S is the unit tangent vector, but the unit tangent vector that you find when your vector valued function is parameterized with the arc length parameter. So usually you're not real lucky where you don't really have your vector valued functions always parameterized using the arc length parameter. And you certainly could do it on your own, because we did that in a previous example on Wednesday. But that's kind of a pain and it takes a long time. It's like, So what's a quicker way? Well, this is my personal favorite right here. I want to put a star by it. I usually use this version of curvature where I find the magnitude of big T prime and I divide it by the magnitude of R prime. And that's a good way to get it. There is another formula that you can use if it's really hard to find big T prime, and sometimes it is. So another way you can do it is, it's just as legit, is you take the cross product of the velocity and acceleration vectors and then take that magnitude, and that goes in the numerator of your quotient, and you divide by the speed cubed. The speed cubed. And I'm not going to derive that one, but if you take a vector calculus class, they'll do the derivation for you. Okay? So let's actually do some problems where we figure out curvature. Now remember, today's material is not going to be on midterm 1. Okay? So don't worry. It's not going to be on midterm 1. Sections 14.4 and 14.5, I'm saving that stuff for midterm 2 instead. So you're only responsible for everything we've done in chapter 13 and sections 14.1, 14.2, and 14.3. And I think we covered 14.3 Monday of this week. So Monday's material this week, you got to know. Okay, lines have zero curvature. Really? Well, if you look at a straight line, I hope you can agree, it doesn't curve at all. So you would expect that the K is 0. Let's just prove it for this particular straight line. And I hope you do agree that this is a vector valued function whose graph would be a straight line, because if you look at each of the components, don't they look like the parametric equations? You know, x would equal 3 minus t, and you know, y equals -1 plus 2t, and they are. So if I'm going to do the curvature, and I'm going to use the big T version. So I'm just going to tell you this problem right now, I'm going to use this version right here for curvature. So I need to go get those ingredients. So R prime, easy to find. It's a constant vector, -1, 2, 7. Nice. And so then what is the magnitude of R prime? Because we're going to need that. So that's going to be, what, the square root of 1 squared plus 2 squared plus 7 squared. Oh my, what's 1 plus 4 plus 49? I think it's 54. And since 54 factors as 9 times 6, and 9 is a perfect square, you can simplify that radical as 3 square root of 6. And now big T is the unitized velocity vector, so let's go ahead and put that all together here. So I get -1, 2, 7 all over 3 square root of 6, and that's going to look like -1 over 3 square root of 6, 2 over 3 square root of 6, 7 over 3 square root of 6. Okay, I'm getting somewhere. And now what do I need to get? Well, I need to get big T prime, because the curvature formula I chose has the magnitude of big T prime as the numerator. Okay, fine. But holy moly, what is the derivative of this constant vector going to be?
0.
It's going to be the 0 vector. Ha! So then my curvature, which is the magnitude of big T prime all over the magnitude of R prime, that's simply going to be 0 all over 3 square root of 6, which is just 0. So boom, we just proved that a straight line has 0 curvature. Okay, questions? Okay, So let's do another interesting example. Let's talk about circles have constant curvature. But before I do, I want to say something and show you a diagram that isn't in your course reader. And that's the benefit of, you know, coming to lecture, because I don't tell you everything in the course reader. Sometimes I do extra. I had a student who needed to withdraw from the class, and they were like, well, you know, can I get all the notes for the course reader? And I'm like, no, you got to be in the class. And even if you did have a set of notes, it wouldn't help, because I do stuff that's kind of outside of the purview. So let me draw two circles here. Those are pretty sad looking circles, sorry. But there you go. Okay. Which one of those circles do you think has a higher curvature, or do you think they have equal curvature?
Equal.
So let's open it up to the chat. What do you guys think? Equal.
They
One
appear to
has,
be equal.
one has bigger, one has smaller. Who knows, huh?
The same.
A lot of people are saying same curvature. Interesting.
The one on the left has more.
Let me pose it a different way so you can think about this. Let's say these were roads. You know, I know that's kind of hard, but let's say these were, you know, roads that you had to drive around. Okay, so if you had to drive around this circle, which would be the one where you'd have to crank your steering wheel a little more in order to maneuver around that road?
Left.
The small one.
Right. This one you'd really have to like crank it, right? Because it's tiny circle. Does that help you kind of define which one has more curvature?
Oh, yeah.
So it turns out that this curvature is higher. So what does that mean? What we're saying is that curvature is inversely proportional to the radius of your circle. So let's say this circle, I'm just going to make something up, had a radius of 2 units. Well, this circle has a radius of, you know, much bigger, let's say 7 units, okay? So it turns out that this curvature is going to end up being a half, but this guy's curvature is only 1/7, because you don't have to crank around as much. And again, if you go back to the definition that we started off today's lecture with, whoops, where we were talking about that something has a higher curvature when the unit tangent vectors as it goes around the curve have to change direction much more often here. So if you looked at drawing these little unit tangent vectors, it has to change a lot more at a point. Whereas if you pick a point here and you look at the unit tangent vector and then look at the point right before it, his unit tangent vector is like pretty much pointing in the same direction. They're not changing and all askew, pointing all over the place. So that's another indicator that your curvature isn't going to be as great, okay? So keeping that in mind, let's actually prove that the curvature, oh boy, I hate it when this happens. This only happens on my Surface Pro. It never happens on my ThinkPad, where you're allowed to erase the actual typing on the PDF file. Interesting. It works? Yeah. Okay, so I'm trying to erase just this mess here. Okay, so let's start from the beginning. Let's do a generic circle parameterization, r cos, r sine. So if we use the curvature formula, that's my favorite, you're going to get r prime, and that's going to be, let's see, the derivative of cos is minus sine, derivative of sine is positive cos, and then if I go ahead and get the speed, which is the magnitude of my velocity vector, I'm going to get r squared sine squared plus r squared cos squared, and then you know the drill, right? You factor out an r squared, and then you use a trig identity because sine squared plus cos squared is
1.
And then this is going to give you absolute value of r, but we'll just say it's r, and we'll assume it's positive. Otherwise, if we have a negative radius, it's not really a circle. Okay, and then we'll go ahead and form big T, because we know that's just the unitized velocity vector. So let's put all of this stuff together. And then after distributing the R and reducing to lowest terms, our big T is just going to be this vector here. And then we got to go get big T prime because that's the curvature formula says so, and that's easy. So the derivative of negative sine is negative cos, and the derivative of cos is negative sine. And now we're ready to get big K because big K is the magnitude of big T prime all over the magnitude of R prime. Okay, so we're going to have, and I hope you can see that the big T prime's magnitude is going to be using the trig identity again. Yeah. And we're done. So the circle with small radius has a larger curvature since it's an inverse proportion. And that's kind of interesting because, you know, it wouldn't be what you'd think because some of you initially thought, oh, they have the same curvature, but it's not quite that. Okay, good for engineers and good if you're a civil engineer to know this. Civil engineers, because if you do any, you know, highway or traffic design, you have to be thinking about this kind of stuff. It's really important. Yeah. I've had some really good students who were civil engineers in my last 10 years of teaching here at Southwestern, and one of them I miss dearly because he was my grader for like 3 years. He was a lot of fun. It's not easy to get a job as a civil engineer. So if you are one, just keep in mind that there are very few jobs out there for civil engineers. The other person who was a civil engineer, Carla, she was great. I had her like over 10 years ago. And she eventually got a job with National City as a civil engineer. And I think she's doing quite well. She was like A++++ student. Very driven. Very driven. Let's look at curvature of a helix. Well, what's a helix? Like if you graph this, it looks like that coil I showed you from before. Like, woo! Okay, so what's the curvature of that thing? Oh, my goodness. Well, let's go get it. I'm going to go pretty quick here. So I'm just finding R prime. Then I'm going to find magnitude of R prime. Well, I'm having some problems today because my computer is again running hot, which slows it down. Is there anything I can do for this? No.
How many programs are you running, Rasky?
That's a good question. I don't know. Let's see here. I'm on the internet, so I'm not really running. Like, I see all these icons down here. Those aren't really running.
Right.
I'm running Zoom, and I'm running, you know, a few internet pages, but I could easily close those out.
If you're, yeah, Google Chrome actually takes up a lot of your computer's RAM.
Does it?
Mm-hmm.
So that's the problem, is what I hear you telling me in your own sweet way. Yes?
From my experience, yeah.
In other words, Google Chrome sucks?
That's a very opinionated thing. I've heard people say that, but personally,
no, it does.
yeah.
Let's be honest, it does. Not only, I mean, my husband hates Google Chrome so much that he doesn't even use it anymore. He uses, have you ever heard of that browser called Brave?
Never.
Yeah.
What?
Yeah. It doesn't track you like Google. You know, every window you open is incognito, essentially, whereas Google tracks you everywhere you go. It's very dangerous, Google.
Huh.
You know, they're all out to get you. Like my husband, his phone has been drained of power like really quick lately, and he found out that somehow some ghost keeps turning on his location, which drains a lot of power, and he's not turning it on. Like he'll just look at it and go, "Hey, how did that get turned on?" And I go, Google's you're on Google's watch list. They're after you. Oh my goodness. Okay, so I don't know. So I'm going to put this all together in one shot here. I don't know, it's still slow. I'm writing on invisible ink right now, so that's why my handwriting is even going to get worse than it usually is. So my apologies.
So if you open up Task Manager, you can see which applications are taking up the most effort to run right now.
Okay, what's a quick way to open Task Manager?
Control-Alt-Delete.
No, Control-Alt-Delete is not going to do it. I'm not buying that one.
No,
nice try though.
It takes you to your main page, and then it should be the very last option under change password for your user.
Okay, you didn't give me a quick way to get the Task Manager yet. I'm listening.
You
Okay.
can search for Task Manager on the Windows search bar.
Here?
Just type in Task Manager.
Yeah, you can do it.
That's another way.
Okay, let's try it. I had a quick and dirty way to get to Task Manager, but it's on my notes at my office, which I'm not allowed to do.
There it is.
Okay, let's see here. Google Chrome. Oh, that is taking up a hell of a lot, isn't it?
So you want to completely exit out Google Chrome if you can.
Well, here's the thing though. Aren't I in Google Chrome through Zoom? Doesn't Zoom go through that or no?
No, Zoom has
No,
its
it's-
No.
Okay. So I can totally get out and not worry?
Yes.
All right, let's find out. All right, let's see if that makes it run less hot. I don't know, my computer is so hot, I can barely even touch it. It's making me sweat.
Quite a bit of other applications open too that are just like kind of hanging out in the background.
All right, well, I'll look at it later. Let's roll. So we need to go get Big T prime. So let's go do that now. It's really easy because you're just going to take the derivative on a component by component basis here. And let's see, the derivative of negative sine is negative cos. Okay. Derivative of cosine is negative sine. And then what's the derivative of this guy?
Zero.
Thank you. That's a pure number. So now I'm going to go get big T prime's magnitude. Sorry, this shouldn't have had magnitude bars. I apologize. Bad notation. I'm going to take away 2 points from myself. Self, you just went down. That is not a magnitude. That is simply the T prime vector. Now we're going to get big T prime. So you're going to take the square root of the sum of the squares of big T prime here. Okay, and we're getting there. We're getting there. So then if you'll notice the two terms that are there, both of them share a like denominator, so I'm going to combine them into a single quotient. And then you'll notice that a squared is going to be a common factor from the numerators. So I can factor out a squared, okay. And then this right here is by trig identity 1. And so this looks like the square root of a squared over a squared plus b squared. And you're almost done. I'd like you to go one more step just to make it look prettier. And then, so then when you simplify the magnitude of big T prime, now you're not done, even though you've done all this work. It's like, oh man, I'm tired. Yeah, me too. So you're going to go, okay, now let's finally use the curvature formula. Yay! And here's what the curvature formula says. Take the magnitude of big T prime, which we just got, and then divide that by speed. Okay, I forgot what that was. Good God. That was the square root of a squared plus b squared. Oh yeah, oh yeah. And then this is kind of yucky looking, so rewrite it as a multiply problem where you multiply by the reciprocal of the denominator, if you think of that guy as being a fraction, and then multiply these two fractions together, and then you'll get what? And this is a constant. So what are we saying? This doesn't always happen. Most of the time your curvature is going to be some scalar function of time t, where it depends on where you're located on your position function of how curvy you are. Curviness will vary. But for a helix, because it's looks like a spring, no matter where you are located on that helix, your curvature will remain whatever that number is. It's a constant. So I want to do one more of these curvature problems, and we're going to use one of the other formulas I put up there. And that one involves a cross product. And why am I going to do that after I've told you that my favorite curvature formula is this one? Because it turns out in this next example, if I did try to find big T prime, it's going to be a nightmare. I'm going to have to use the quotient rule with the chain rule like multiple times, and it's going to be really a lot of painful algebra. And I could do it if I like pain and get the same answer. But if I want to circumvent some of that awful pain, then I'm going to use an alternate formula. So I'm going to use in the next example this formula here, which is still a little painful because I do have to do a cross product, which can be kind of yucky, but it's not going to be as bad. So it's going to be the preferred choice to get curvature for the next problem. Okay. So it's curvature of a parabola. So if you actually did use your graphing calculator and graph that, that is a parabola oriented in the direction from left to right. Not too hard. What's the curvature? Now the curvature varies because it depends on where you are. Like if I'm over here at this point, call it P, I'm not curving around too much. On the other hand, if I'm close to the vertex, there's a lot more curvature going on over there at the vertex than there is on other points. So it's going to be a variable curvature. So let's go ahead and get the curvature, and then we'll also ask an interesting question: when is the curvature maximum? And visually you can tell it's going to occur at the vertex, but prove it analytically. And then we'll find the position and value for which the curvature is maximized, both the position and the time. Okay, so first up, let's go get our prime. That's super easy, 2t, 0, and 1 if I do component form. Why is this 0? I thought this kind of looked like a 2D curve, and it is. If you're looking at 3D, this is actually in the XZ plane.
There's no J.
Yeah, there's no J. J is gone. But he's still there. He's
It doesn't mean.
he's still there. Okay, he's hiding. So now, since I'm going to go use that alternate curvature formula with a cross product of velocity and acceleration, I got to go get acceleration. But that's easy because it turns out it's a constant vector. Does that always happen? No, but it does here, which is awesome. Now I can go get R prime cross product with R double prime. So I do that 3x3 determinant method, please. I do this nicely and have notation that's nice and beautiful, otherwise lose points. IJK goes across the top. The R prime vector goes along the second row, and the third row is the acceleration vector. So it's going to turn out, let's do this on the fly. 0 minus 0, I'm going to get 0 I hat. Minus 0 minus 2, j hat. Plus 0 minus 0 is going to be 0 k hat. Ooh, nice. So this is going to end up being just 2j hat, which if I write it in component form as component 0, 2, 0. Okay, fine. Then what? Well, the curvature formula says, hey, go get the magnitude of this cross product. That's just going to be square root of 2 squared, which is 2. Fine. Then what? Go get R prime of t magnitude, because that's the something that we're going to end up having to I think we're going to have to cube that guy. So let's see here. Our prime is going to be the square root of 2t squared plus 0 squared plus 1 squared. I get square root of 4t squared plus 1. Okay, now let's go look at that formula again. Make sure we got all the ingredients. Wow, it's way back there. Where is it? Ah, here it is. Okay. So you're going to take r prime magnitude and cube that in the denominator, and the numerator has the magnitude of the cross product. Okay, make sure we plug all these folks into the right spots. Get a note to myself here. Where are we? Okay, we're down here. Ah, okay. So now we're ready to do k is the magnitude of r prime with our double prime, which we got, that was a 2, and we're going to divide that by magnitude of r prime cubed. And so for us, that's going to be 2 all over the square root of 4t squared plus 1 cubed. Okay, so it is a function of time t. It's a scalar function. And where do you think it's going to be maximized? So when is this the max?
For r prime equals 0. Oh, that.
So if you look at the denominator, do you notice it's always going to be a positive result? You're taking the square root of something and then you're cubing it, and the square root is going to be hopefully positive, not 0 or negative. And so when is this quotient maximized? Well, you want your denominator to be as small as possible, because the larger your magnitude of your denominator grows, then it's going to cut down on your curvature, because it'll be a tinier and tinier fraction. So the real question is, when is the denominator maximized? Or actually, I should say minimized.
At time equals 0.
Yes, at time t equals 0 is when it's going to be the smallest it can possibly be. So at time t equals 0 is the answer. That's when you're going to have maximum curvature. And where are you located on this parabola? That's parabola in 3D. If I were to really draw this parabola correctly here for the people that aren't here, here's x, here's y, here's z, and this curve lies in the xz plane. And actually, I think is a sideways parabola. So I think it's going to look like we've got x equals t squared and z equals t. So it's probably going to look something like this in the xz plane. So right here I claim this is t equals 0, and that's at the point 0, 0, 0. Is when this curvature will be the most, okay? And we're done with that problem. Okay, curvature of a parabola, there you go. And you'll have one of those on your My Math Lab homework. So I've already done one for you, so it shouldn't be really hard for you to do, okay? So I'm done talking about curvature, and I'm going to do a new topic right now, but I'm going to take a pause and see if we have any questions or issues.
When that t was equal to 0, you looked at the denominator. I was wondering if you could have used the calculus 1 method where you take the derivative and set it equal to 0.
Oh yeah, go ahead. Yeah, go do k prime equals 0 or undefined. Yeah, you can treat that as a calculus 1 problem. Absolutely. But I wanted to do it by inspection.
Okay.
Quicker. Okay, anything else? Okay, so looks like I erased something that I didn't want to erase. The last little piece of this section is something that is near and dear to physics folks, and it basically talks about the fact that the acceleration vector is always going to be a vector that lies in the same plane as big T and big N. So if you're thinking, oh, wow, you know, this big T and big N, what's this got to do with anything? Well, I hope I've convinced you that, for some, you know, big T and big N are important in physics because you've got the T and B frame. And then we do use the concept of big T prime to help us get curvature. But this is the last idea in the whole module on vector valued functions. It's really important. So what we're saying is this right here, is that any acceleration vector, and this should be a vector here, can be written as a linear combination of the unit tangent vector and the principal unit normal vector. Whether it's a 2D or a 3D curve, you don't care. Now the coefficients here, those are scalar functions, and those are sometimes tricky to find. But and there's many formulas for them. If you take a vector calculus class, they'll not only derive every single formula ad nauseum, they just go on and on because they're going to like hit you with this and all these sacred formulas. But I just kind of want to do sort of the highlights of it so you at least have seen it for your education. So this is the key point. The acceleration vector always lies in the same plane as the unit tangent vector and the unit normal vector. So if here you are in 3D and you had some weird funky curve like that, and you were able to find big T, say, was doing that, and let's say big N was like pointing over here because it's orthogonal. It turns out that and if this were to create its own little flat plane right there, you guys know what a plane looks like, you are guaranteed, like this is, you get this for free, people, this fact will be free, that the acceleration vector lies on this plane somewhere. You know, I'm just going to draw something, you know, who knows, maybe acceleration vector is like that for that particular curve, who knows, but it's in that plane. The a sub t, the coefficient there, the component for t, is basically the rate of change of speed, also known as the rate of change of arc length. So you can kind of think of that too, because arc length depends on speed. And there's all sorts of formulas, and you'll see when we do the formula. The a sub n guy is a function of both speed and curvature. And so there's all kinds of formulas for these guys. So if you're driving around a turn here, this a sub n, you know when you drive your car around a turn, and if you're driving really fast and it's a really sharp turn, do you ever feel yourself pushed up against your car door or anything? That's this component coming into play, okay? So the way that I like to find the a sub t and the a sub n, if somebody asks me to, is I like to use projections, because it's just going to be basically the scalar component of projecting your acceleration vector onto the unit tangent vector. And this guy, you remember projections involve dot product. And the a sub n is just the scalar part of the acceleration vector projected onto the unit normal vector, that's all. But if you want to see some of the other fascinating formulas that you can use to get a sub t and a sub n, these are my personal favorites, but if you want to knock yourself out, here's some other ones. And they're all good. They're all going to give you the same result. But there you go. So that's all that stuff into one big package. So we're officially done with chapter 14. So I'm going to pause there and see if you guys have any questions. I'll check the chat. Anybody chatting? It's filled with lava.
Yeah, have you noticed a performance difference in your computer, or is it just still the same?
I think it's a little bit better, Nick. Thanks for asking. Since I closed the Chrome out. It's not giving me that long 10-second delay after I write something down. See, that's something that just drives me nuts. When I'm writing on the screen, I like to see my handwriting show up, in real time. But when it slows down, I'll be writing and it'll take like, 5-10 seconds for the writing to catch up. So it's like I'm writing in invisible ink. Hilarious.
That sounds maddening. Does the Surface Pro require like driver updates every once in a while, or I'm familiar with how those things would work?
Maybe, but anytime I shut it down, it always does its own updates.
Okay.
Microsoft, is hooked into
Yeah.
Microsoft, and so I agree with you, David, that I think that maybe our phones and our tablets and our laptops will detonate at a certain time deemed appropriate by Bill Gates.
I'm waiting for the day.
Well, he'll also make it happen faster since he's funding the vaccine.
Terrifying.
Just please blow everything up after I get out of school. I don't want to be a student in the middle of the apocalypse, and I'd feel like I've done absolutely nothing with my life.
Yeah, but you won't care because you'll be dead. So what would it matter?
That
Sorry
5
to rain
seconds.
on your parade. I didn't mean to bring it down or anything.
The 5 seconds of yay, I did it.
Oh, you want that 5 seconds of yay?
Yeah.
What if I told you it's only going to last 30 seconds? Would that change your mind?
It's 25 extra than what I was bargaining for.
That's 6 times as much. Come on, man. Like,
Yeah,
you have to look at the positive.
it's kind of like, when you're on a diet and you're like, and then you start cheating on your diet, like, well, I really need to eat that cupcake or whatever. But the cupcake only lasts for maybe, depending on how fast you eat, 35, 40 seconds, maybe a minute, and then it's done. And then now you screwed up. Okay, so I'm going to start chapter 15 right now if nobody has any questions. So let's just do a quick recap of what we've done, and this might help you get ready for your midterm, okay? So I'm going to put on pause because this has nothing to resume. Okay, what do you know how to do? Well, you know that there's a couple functions that you studied, Calc 1 and Calc 2, as well as pre-calc. You studied functions of a single variable. Like y equals f of x. That's a function of a single variable. And what's the second type? Well, we just got done with a whole chapter, chapter 14, brand new function we looked at, vector valued functions. So let's draw the function machines again. I've already done this, but I'm going to do it again, at the risk of being redundant, because I want you to see all the flavors of all the functions I'm introducing this semester, because we're not done. Today we're going to learn a new one, and then we'll learn another new one when we get to vector fields. That'll be chapter 17. Okay, so quick review. Here is a function machine for a function of a single variable, okay? So you remember that we discussed this before, the domain and range. The domain consists of what? Are you going to give it a point, a real number, or a vector? What do you feed one of these functions of a single variable? Does anybody remember? Here's your 3 choices again. Do you feed it a point, a real number, or a vector?
Real number.
Real number. Yeah, like you give it x, like x equals 2, and it goes, thank you, x equals 2. And then the range is consisting of what? Points, real numbers, or vectors?
Real number.
Real number.
Real numbers, right. So you feed it a real number, poops out a real number. Okay, we're done here. The other function that we just learned back in chapter 14, these are vector valued functions, and I'll do a 3D version, but you can have 2D or 3D. So here's a look of one of them with the notation. Okay, great. So let's talk about the domain elements here for this function machine. What do you feed a vector valued function? Do you feed them a point? Do you feed them a real number, or do you feed them a vector?
Vector.
Feed him a point.
You feed them a point. You give them a value of t, like t equals 2 or something. You give them a real number, excuse me, a real number, not a point. Real number. You give them a real number like time t equals 27 or t equals negative 0.5. You give him a real number, and then he slurps it up, Yum. And then what does he poop out? A point, a real number, or a vector?
Vector.
Vector. So I want you to look at this. This guy, you feed it a real number, he poops out a real number, okay? And you did that function. That's the relationship between the domain and range is, you know, your domain and range, both are sets of real numbers. This has a little different flavor because the set of elements that you give it are real numbers. You feed it real numbers, and it goes, and it poops out vectors. Okay? So that's interesting. So now we're going to introduce a brand new function, and we'll do a function machine shortly, but you're not ready yet. Let's lay down some of the laws. Okay. We're going to talk about functions of more than one variable. Okay? You probably have not seen this notation unless you've taken this class already, because they don't ever do it for you in a pre-calc or a calc 1 or a calc 2 class. But here's an interesting thought. You actually have worked with functions of more than one variable very often. Really? Yeah, like for example, you've seen like, well, you've seen this one. How about volume is equal to length times width times height? When you look at the a volume of a rectangular box, say, that's a function of 3 variables. Sure. Volume equals pi r squared h, that's the volume of a right circular cylinder. That's a function of 2 variables, radius and height. And we actually did one when we talked about work being force times distance. Force and distance are 2 variables, so there's 2 variables. So now let's look at notation. When you're doing functions of more than one variable, you use this notation, f of parentheses, and inside the parentheses, you put your variables, your independent variables, delimited by commas. So for this example, and you're calling it z, z is equal to a function of x and y, and in this case, they're just giving you an example of a function of x and y, x squared plus xy. Okay, that's a function of 2 variables. Great. Now the notation for a function of 3 variables, and they typically call it w equals, because you've already used up z here as one of the independent variables, a function of x, y, z, and here's just an example of a function of x, y, and z, x plus 2y minus 3z. Great. Now both of these examples that we're just looking at here real quick for notation purposes are known as functions in explicit form. And that's important because later on we're going to have an idea of functions in implicit form. Really? Well, yeah, and you've done that already. So just a little side note for those of you who forgot your Calc 1 already. When you did Calc 1, you talked about explicit functions of a single variable, like y is equal to, you know, x squared minus 7x plus 1. That's an explicit function of x. But there are implicit functions that you can't even solve for y, even if you're a hotshot mathematician. Like, check out this implicit function. Sine of x plus y minus y cubed is equal to e to the xy plus 17, just say. Oh, good God, man. An implicit function of x, and you could find dy dx, but you'd have to use implicit differentiation. Do you remember that from Calc 1? Oh, yeah.
Did it just freeze?
Could be.
Yeah,
Oh,
for a split second.
Am I still frozen?
You're good now.
You're good.
Okay. I don't know. My internet's looking pretty low today. I could blow out at any time.
After class,
It just
Professor,
could happen.
I think I have another way to fix your internet, but I'll tell you after class.
Oh gosh, bless you. You're hired. Okay. But if David's right, then my Surface Pro is filled to the brim with Bitcoin.
Oh no, we're losing her.
Oh my God! Holy fuck! That's
David, what the fuck?
Oh no!
I mean,
Guys,
sorry.
calm down.
Okay.
Am I gone?
No, I thought
You're
the CIA
like coming in and out. Definitely.
I thought the CIA blew you up.
I shouldn't have mentioned Bitcoin miners, right, Nick? You're right. I blew it. Now that I'm on their watch list. Oh, shoot. Are you guys still there?
Yes.
Yeah.
Yeah.
Yeah, all right. Okay. The mention of Bitcoin miners. Is my GPS on? Oh, hold on a second. No, it better not be. Now, my phone is downstairs. I try to keep my phone far away from me because remember I told you it lowers your IQ? The closer your phone is to your brain, the more IQ points you lose. And I don't need to lose any IQ points right now, okay? This pandemic has probably already taken my IQ down at least 10 notches. Okay, let's do two variables written in explicit form. But before I do you guys remember when you're doing a function that's written explicitly, do you guys remember that if you have f of x equals, say, x squared, isn't it legal to replace f of x with y and say y equals x squared instead? Yes or no?
Yup.
Yeah, that's totally legit. So I want to take that and extend that idea to 3D. So if you're given a function of two variables like f of x and y, it is legal for you to equal some stuff. You can also say z equals that stuff just as easily, okay? So that's explicit. Now sometimes when you're given an explicit function, I'll just do a quickie example, like z equals x squared plus xy. A lot of times they want you to rearrange it where you get all the crap on one side and 0 on the other. And if you do that, let's say I move the z to the other side and get 0 on this side. If I do that, then this right-hand side is a function of 3 variables. So when you do that, a lot of times they'll call this crap big F, and he's a function of 3 variables. And that might mean, and sometimes what you'll see in the book is it's written as the function that was of 2 variables minus z equals 0. So that's a function written implicitly. So when do you use which one, and does it matter? I will be very clear when you use which one, okay? So you won't have to guess. Just do your homework and stay in touch here. Okay, let's do a quick definition, and then we're going to do a function machine for a function of 2 variables. So here's the official definition of a function of 2 variables. If you have a function, z equals f of xy, what it does, it assigns to every point xy that lives in R2, R2 is 2 dimensions, it assigns a unique real number z that's in a set of real numbers, okay? So here is sort of a picture of the relationship. So here's your domain here in the xy plane. So the domain consists of little points, little dots here in the xy plane, and z is like a mapping, and z maps you to real numbers, where the output, the poo-poo, is a real number. So that's a nice diagram that sort of gives you the relationship between the domain and range. So I'm going to draw a different diagram relating this with this relationship. So here's our function of 2 variables. What do we feed him? What are the elements of his domain? And I already answered it here in this previous diagram. What? I'll give you a choice. Are they points, real numbers, or vectors?
Real numbers.
Points.
They're points. You feed it an actual ordered pair. It eats a point, and the poo-poo is a real number. So the points live here in R2. They come from a 2-dimensional domain. And the poo-poo, the output, is a pure real number. Now, why would you care about this? Well, it's going to happen. What we're going to be doing when we graph this in 2 shakes is you'll feed it a point. Let's say this point right here, I'm just making something up, 2, 1. And the output, or its corresponding height or altitude, will be this height here. And so when we graph the function of 2 variables, it's going to be a collection of heights that are hovering over your domain, and you're going to get like some surface up here in 3D. And it'll be like a capping surface, as an example. Here's a surface in 3D, like a mountain. And so that is one way to think about a function of 2 variables, where its graph is a surface, where the heights are graphed that hover above the points that you feed it. So moving on, let's just do some quick examples and then we'll wrap up today's lecture. And you're going to take an exam for me on Monday, so I won't be seeing you again until Wednesday of next week, where we'll pick this stuff up again after. So hopefully, let me just get through a little bit more, and then next week we'll do domains, level curves. We're going to do limits again. Oh yeah, limits again, only high power, and then we'll do some partial derivatives. I want to give you an announcement here real quick before I forget. Did I close out my announcement page? No. Another announcement I should probably tell you in advance so you don't freak out. So next Monday, you're taking an exam. There's no class. The Monday after that, September 28th, which is a Monday also, there will be no class. It's a Jewish holiday known as Yom Kippur. So I'm going to be in a synagogue praying. Special day. The good news is you're not exempt from the material. I created a whole bunch of videos for you on the topic that I would have been covering that day, partial derivatives. And they're already in Canvas. I got them closed captioned for you also. So that day there won't be any Zoom lecture, but you'll watch some videos that I've posted for you in Canvas on that day, okay? And I still think you're taking a quiz for me that day, or it's due that morning. So you're not like, it's not like anything else is stopped. Let me just see where we're at here. If you look at your syllabus, I'm just looking at it right now. You have a quiz 2 due that day at 8:30 in the morning. No, wait a minute, hang on a second. Quiz 4 due that day. Quiz 4 is due. So you still have a quiz due that day, so you don't think you're like getting out scot-free, okay? But you don't have to do a class that day with me. So any questions on that?
Crystal clear. Thank you.
Wait, really quick
Just so you
question.
know. Yeah,
The exam Monday, it's due at 11, and how long is it?
it's a little over 2 hours.
Okay.
The extra 11 o'clock isn't from my math lab. I'm just giving you a chance to take photos and upload your work, right?
Is it only available is it only available at 8 in the morning?
8:15.
All right.
That's the start time it's open. You can start later, but not
That's
much
why
later. Like I wouldn't start, listen, I wouldn't start more than 10 minutes past 8:15, because then that's going to cut into the time that you're allowed to actually take the exam.
Okay.
Do you know what I'm saying? Because this is a tight window, and there's a reason for it. Fluency and academic integrity. Look, you know, MIT, you know how I give you those nice 24-hour windows for the quizzes? That's my gift to you. You don't get that for the exams. All right, so how do you evaluate a function of two variables at various points? Well, just plug stuff in. So if you're going to evaluate the function at 3, 2, here's the notation we use. Anywhere I see an x, I'll substitute a 3, and anywhere I see a y, if this is the given function, and then what is the value that comes out there? I think 27 minus 4 is equal to 23. So there's the answer for letter A. Beautiful. For letter B, okay, I'm going to evaluate the function at -1, 4. So the notation would be f evaluated at -1, 4. And then you substitute -1 in place of x, and you substitute 4 in place of the y, easy peasy. And I get -5. Now, what if you're asked to evaluate the function at a point where one of the coordinates of the point is just variable? Well, you can do that, then same thing, just substitute. F evaluated at 5y is 3 times 5 squared minus 2y. And so for this particular case, it's 75 minus 2y. And similarly, if your x is variable, okay, f evaluated at x2 is going to be 3x squared minus 2 times 2. All right, I get 3x squared minus 4. Okay, done. And now the difference quotient. I love putting these on exams because I get all kinds of wacky answers that have nothing to do. So this is similar to the limit definition that we're going to be coming up on soon when we do partial derivatives. You want to know how to do this. So it's real easy because the first part of the numerator, you're going to evaluate your function at this weird point with x coordinate x plus delta x, and then the y coordinate is just y. And then you're going to go minus, and then just the function of x and y itself. But they gave you the function of x and y. It's just going to be 3x squared minus 2y. Okay. And that's all over delta x. And I'll give you 1 point out of 10 if you get this far, but now clean this mess up. And now it's just algebra. So don't distribute this 3 yet. You still have to FOIL that guy out. I'm going to distribute this negative. I'm going to expand x plus delta x squared, and then I'll FOIL it. And then when I distribute this negative here over the difference, and then I simplify, it looks like some things are going to cancel. Well, negative 2y adds up to 2y gets 0. This thing here, after FOILing, I'll get x squared plus 2x delta x plus delta x squared. And then I still have the minus 3x somewhere in there. Then what? And I think that should be minus 3x squared. My bad, sorry. And this is still all over delta x. And now you can distribute this 3 over the brackets, and I get 3x squared plus 6x delta x plus 3 delta x getting squared. And then I still have the minus 3x squared. That whole mess all over delta x, the 3x squared minus 3x squared adds to 0. And so what do I have left? I have this, but you can simplify that further by factoring out a delta x from the numerator and reducing this to lowest terms. So when I do that, the delta x's reduce out to 1, and my final answer is 6x plus 3 times delta x. And I know that looks really weird, but the idea is, hey, when you're doing one of these difference quotients, because later on we're going to take a limit as delta x goes to 0, and that's going to give us a partial derivative. I think this is a good place to quit. So I'm done. I'll stick around for a few minutes for any last minute questions. Remember, I do have office hours today between noon and 2, but that's your last chance to ask me questions. I don't answer emails over the weekend. So don't, email me over the weekend and go, oh, hey, I still don't get lecture, whatever, or I'm having trouble with my math lab problem. I'm going to not respond. Okay, I don't respond on weekends to those kind of questions. The only thing I would respond on a weekend is like some huge emergency, like my math lab crashes. That's maybe I'll respond. Also keep in mind the Jewish high holidays are starting at sundown tonight. And so my whole weekend is I'm with family and doing a lot of praying. I'll pray for you, okay? I'll keep you in my thoughts and prayers for doing fantastic on midterm 1. Okay? Shana Tova, Happy New Year. I'm going to stop the recording. If you want to ask me a question